Okay, so now we're recording. So last meeting, we started talking about supervised learning algorithms. We discussed three of the most popular algorithms: the naive Bayesian classifier, the decision tree classifier, and the KNN classifier. And we were able to illustrate a MATLAB code that implements the naive Bayesian and the uh, the decision tree algorithm. So for today, my plan is to show you a quick code or a short code implementing the KNN algorithm and play a little bit with the parameters involved with it. And I will introduce you to the Matlab Learner App, which could be a nice tool uh, for you to use for the problem set that I just gave over the weekend. So in that light, we can also talk about the problem set and see if you have some questions about it, right? And then that will be the course for us, but I'll be open for consultations. If you need some help with your project, let me know. I will suggest to Dr. Jomar that the deadline for the project would be at the day of the final exam. Depending on when it will be scheduled by the registrar, so that you will have ample time to do it. But again, I'll be open for consultation, online, face to face, or hybrid, whenever you need help with the problem set. All right. So let me share my screen and let's see the MATLAB code I have for the KNN algorithm. But just a quick recap, the KNN algorithm actually is a simple one that computes depending on the distance you the distance you choose, or it first finds what are the k nearest neighbors, and that's what KNN stands for. So you input the value for k into your algorithm, and then what the algorithm will do is that it will find the k nearest neighbors to your query point, right? Depending on what type of distance you're using, and then it will take a vote, or it will survey how many k or how many of each class are there in the k nearest neighbors, and the class with the most representatives among the k members that are closest to the point will be the the winning class. All right. So that's how you choose what's the probable class of a query point. So it's really finding the class that constitutes the most out of the k nearest neighbors in k nearest neighbors of your query point. Okay. Now let's see. I hope you can see my MATLAB screen, and I hope the size is good. Okay. So I just have here the usual loading procedure. I load the database. So in your problem set, you'll just need to find a suitable database. Then you can load it either using this command, or just input the matrix of measurements and say species list on the workspace. So just load it in. And then I would just like to see the scatter plot of the measurements, actually a colored scatter plot, where I plot the petal length, which apparently is the third column in the matrix mesh inside the Fisher-Irish dataset, and the petal width, which is the fourth column in the measurement matrix. And then I want them to be colored according to the species. So that's really what this inputs to the um, gscatter command does. And then I'll just put labels to it. So let's just run the first 8 lines of the code. So I highlight them and I pressed F9. And hold on, guys. Okay, there you go. This is our data set. And our uh, our our KNN algorithm has access to it. All right. So because it's a supervised learning algorithm, so it specifically knows that those data points within this group, all right, grouped together with respect to petal length and petal width, will belong to setosa. This ones will belong to versicolor, and the rest, the yellow ones, belong to the the Virginica variants. So our our uh, our algorithm has perfect access or has complete access on this data set, all right? So it's just to visualize the data that we have. We feed this into our algorithm, and then we will train the algorithm, the KNN algorithm, to be able to, uh, to classify measurements, all right? Now, in line number 10, I just minimize the matrix mesh or the amount of data that I'm going to use. Remember the matrix mesh, if you look at the workspace over here on the right panel, so here, you see that the mesh matrix is 150 by 4. You have 150 specimen with 4 measurements for each specimen, all right? The third and the fourth columns are the petal length and the petal width. So the first 2 columns are the sepal length and the sepal width. But I want to train my algorithm only using the third and the fourth columns for all the rows. So again, remember, if you want to concatenate or if you want to, how do you call it? If you want to downsize a matrix, but you want to keep all of its rows, you put a colon in the first argument of the matrix, and you put the columns you want to keep on the second argument. So 3 column 4 means I'm keeping the third to the fourth rows of the measurement matrix into the new matrix X. And that's what I will feed into my KNN algorithm, right? And then the vector Y consists of query data. So here I want the KNN classifier to predict what is the variant of a specimen or an Irish flower with petal length 5 centimeters and the petal width 1.45 centimeters. All right. Now, and then I'll start doing the KNN search or the KNN algorithm. Now, remember that we need to feed the algorithm with the parameter K. Remember, the parameter K is the number of neighbors that we will consider in the sort of notation later, right? So you need to declare how many members. Well, there is no hard and fast rule in selecting the value for K. If you use a large value of K, then that means we're considering a lot of data points, but that could be costly. All right. So that's why the higher K is, the most probably the most accurate your prediction would be. However, when you use a large value of K, that means you're almost considering the entire data set, and that would be computationally expensive. So it's like a brute force technique, right? So you don't want K to be very large, and you don't want it to be very small, because if it's too small, then that means you are just basing your prediction on just a few of the neighbors of the query point. Okay. Now, you can choose the value of K, but I read somewhere, I just forgot where, that a nice choice for K is the ceiling of the square root of the number of specimens. So in this particular case here, I'm using K to be the square root of X. But of course, X is not necessary. This is the number of rows of, not the number of rows of X. So that means K was computed here to be the square root of 150, because our matrix X contains 150 data points. I take its square root, but it is not necessarily, a whole number. K must be a whole number because that represents the number of nearest neighbors that you want to use. So I'll take its ceiling, the least integer greater than or equal to the square root of 150. So if you take 150, you take its square root, you get what? You get around 12.247. And then the ceiling is sort of rounding it up. So this will be equal to 13. So I'm considering the 13 nearest neighbors to the query point Y, and I will count how many of them belong to Setosa, belong to versicolor, belong to Virginica, and then the class with the highest number of members within that neighborhood of 13 data points will be the predicted class, right? Now, I think it's still easy to do it manual or to program it manually, but why would you program it manually if MATLAB has a one-line command for it, right? So the syntax is KNN Search, okay? And then the inputs are the following. So the first input would be the data set that you want. So that's our matrix X. And then the next is the query vector Y. So you can add some more points to the query point Y. So the rows in the query point Y represents the specimen. So here I only have one row. So that means I'm only asking the algorithm to classify one particular specimen. And then here you need to give the name argument pair. So first I want to declare the value of K, which is essentially how many neighbors you want to use. And we have computed that before in line 13 and stored in the variable K. So after the string capital K enclosed in quotation marks, you put the value of K that you computed. Then you can also personalize this by telling the algorithm what kind of distance to use. Because again, you're taking the K nearest neighbors. But what's your reference for determining which are the nearest neighbors? So you need to specify what kind of metric, what kind of distance you're going to use, right? So there are several options that could be tailor fit to your data. All right. Remember, we discussed distances and we know, or we have sort of some idea when is one distance more applicable than another. So take a look at that. So in this particular first run, I'm going to use the Euclidean distance. All right. And then there's just some points here that I want to use to to say visualize the data. So I will append line 17 to 19, simply append to the query point the data point. Okay. So that we can see where is the query point relative to the data point. So if I'm going to run line 17 to 19, but I need to run what? I need to run 10 and 11 first. So I can run 10 and 11 first so that I get the matrix X and the vector Y. And then now I can run lines 18 and 19 so that we get scatter plot. And that will be in this table. All right. So you see the block dot in this figure. Can you guys see the figure right now? Or no? Okay, there we go. It's a little bit delayed on my end, but I'm seeing it now on my tablet. So you see the block dot over here. All right. That's the point that we are trying to classify. All right. So we want to know whether it's setosa, versicolor, or virginica. All right. And then remember, we computed K. The value of K is 13. And we imposed the Euclidean distance. So the KNN algorithm will look for the 13 nearest neighbor of this data point. And the metric that's going to be used is Euclidean distance. So basically, it's the usual distance that we know, right? So probably this will be one of them. This will be one of them. This one, another one. Count the number so count 13 of the nearest neighbors, and then decide how many of them are Bracetosa, versicolor, or virginica. And the one with the most counts will be the classified or the predicted class, right? It's that simple. Okay, then let's see what's next. Well, the KNN search will give me the predicted class in terms of an index number, IDX. So it will tell me, is it species number 1, species number 2, or species number 3, right? So that's what the index will give me. So let's run this. I need to run 13 and 15. Okay. And if you look at the workspace, I have IDX is 1 by 13. Okay. So 1 by 13, this tells me what are the 13 nearest neighbors. All right. So IDX, the output of line 15 stored in IDX is the vector consisting of the labels for the 13 nearest neighbors. So that means specimen number 120, specimen number 53, specimen number 73, 134, 84, 77, 78, 51, 64, 87, 57, and 57, 124, and 128 are the 13 nearest neighbors. All right. So IDX gives us a list of the 13 nearest neighbors. And then let's see. Okay. And then I want to compare. I want to know what are the actual labels or what are the actual species of the 13 nearest neighbors. So what I did here, I think this is a sort of a very I did it manually. I'll try something that will do it in one line. I just realized it can be done in one line, but this is me trying to do it manually. So I created a species list, an index of the species. So that means I have the first 50 data points are belong to species number 1. The 51st to the 100th data point in the matrix X belong to the second species, and the 101st to the 150th belong to the 30th species. Okay. Then let me do that. Let me just plot the query points and its k nearest neighbors, and then I'm going to run this also. Okay, so this figure number 4, shows us what are the 13 nearest neighbors with the x and the y axis, the petal measurements, and with the labels on the neighbors, right? So here we have a virginica, another virginica, a versicolor, a bunch of versicolors all over the place. Do I get 13? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I only see 10 points, probably because some of the data points might overlap. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. So that's why we don't see all 13 points, because some of them might have overlapped. So that means there are specimen of the same measurements. I hope that's the case because I can see all of them. But we have a complete listing of their indices. So probably that's the case why I only see a few. And then in line 30, I will compute the mode of the species, the labels inside species list corresponding to the index. So I will get the index. Remember, IDX contains the 13 nearest neighbors. If you will use that vector IDX as input to the vector species list, this will just collapse the vector species list into a vector of 13 points whose components are exactly the components in the same position as the vector IDX. For instance, let me just run this command, species list index. I'll press F9. So I'll get 13 numbers, 3, 2, 2, 3, 2, 2, 2, 2, 2, 2, 3, 3. That means these are the labels of the 13 nearest neighbors. So, and then I'm just going to get the mode of this vector. Remember, the mode is the most occurring or the most frequently occurring observation. So that means most frequently appearing classification among the 13 neighbors is classification number 2. I'll get to my answer key. So the predicted species is versicolor. All right. So let's see how fast this run. So if you want to experiment with respect to time, so you just put tick at the to start the timer and the talk to stop the timer. So let me just clear and close everything. Let's see. So here our K is 13. So let's see what happens and how long it will run. So it ran for 0.8177 seconds. Maybe let's note that. I just want to see how the effect of increasing K to the time is. But I don't think this will matter too much in our experiment because we have a very small data set. But imagine if you have a data set of, say, millions of data points, then it will be very important that you choose K wisely. So here, when K is 13, we get versicolor. And we do that, or we get that after 0.81 second, right? Let's try to increase K. So say I replace K by 25. Let's see what's the effect of that on the running time of our algorithm. I'll press F5 again. So it seems to be faster for some reasons. So K is 25. Again, it predicted versicolor, and it ran for 0.32 seconds. That's odd. Maybe that's a timing issue for my laptop. Let me do the ceiling again. F5. Yeah. The ceiling again gave me 0.31 seconds. So maybe that's 0.31, not 81. I don't know why, but the run there has been longer. So 0.31 seconds. Let's say K is 100. Yes, I can make K 100. And then run this. Just 31 seconds. Or maybe I should clear and close to see how fast it is working. And this is a failed demonstration because I wanted the algorithm to run faster, or sorry, I expected that the algorithm will run slower or will run longer when I put a large value for K, because that entails much computations, but I don't know what's happening. Probably it's because of how my laptop is working. But anyway, so yeah, it's using some of the GPU or RAM issues. But anyway, but but in terms of complexity, a raw count of the number of operations to be performed, we want K to be right about between the middle, right? So we don't want it to be too large. We don't want it to be too small. Another reason why we don't want it to be too large is that if it's too large, then you will considering all the data points. So imagine our data there, we have 150 data points. And what if like what I did here, I use all 150 data points. So you look at this case 150, that's the entire data set. So that means we're looking for the 150 nearest neighbors to the query point. But that will encompass all of our data points, right? And so the more the classification or the class with the most specimen will give us the mode, right? And in that particular case, oops, sorry, what happened here? Okay, but what happened here in the data set, majority of the data points are in the Setosa variant. And that's why you see here, the predicted species is Setosa, even if the Setosas are all the way here in the lower left corner. Okay, my pencil died. So the blue dots, which are very far away from the block dot that is our query point, right? So the predicted class is over here. And the query point is over here, right? So that's another danger of using a large value for K. All right. Oh, there we go. So there, and there's our query point. Okay. Now let me try this. Uh, this. Uh, Let me try this scheme. I don't know if this will work. I'll copy paste the predict command here. I don't know if this will work. So maybe I'll run it here. So I'll use predict. Here I didn't create a model. Let me see if in KNN I can create a model. Yeah, that's the problem with KNN. It doesn't create a model, unlike the the naive Bayesian and the decision tree algorithm, where you create models and then you can just use the predict command. I was hoping that I can use the predict command also for the KNN algorithm, but I can't use it because in the predict command, I need a model, right? A model structure. But KNN doesn't create a model structure. It will just give us the actual predicted index. It will just give us the k nearest neighbors of the of the um, of the query point. All right. So, are there any questions about this code or about how it works? All right. None. So, if there are none, then let me go ahead and show you quickly the Matlab Learner App. Let me just probably I can go here. So if you download the data science or the machine learning toolbox, it should appear here in the apps ribbon. So in the apps ribbon, click it and then look for the classification learner. So I got the classification learner over there. Then you can click on it. Let's just wait. It's gonna load for some time because it's the first time I'm using it. So it will load all the packages it needs. Okay, so here's the classification learner. It will open another tab. It's a standalone app, right? Standalone in some sort. So to start, you click the new session over here. Okay, you click the new session. It will open a dialog box, which will ask you to input or to it will ask you to import some data. So here, first, I need to select what are the data set variable. So remember, in our case, our data set variable, say I want to use the complete data set. But look at the title of the command, look at the title of the dialog box. It's new session from workspace. So before you open the classification app, you need to load the data set into the workspace, right? And then once you open the new session dialog box, it will give you the option of declaring what is the data set that you will use. And the options there would be all those variables inside your workspace. So these are the remnants of my workspace from the previous run, but I want to use as data set the entire measurement matrix, right? The mesh, the 150 by 4 matrix mesh. So I'll put that there, okay? Then MATLAB will give you some more options. But take a look at the response. The response is really the key. This will tell you the actual classification of the actual classification of the data in your measurement matrix, right? So here, since it is not from the dataset variable, so if it's from the dataset variable, it will ask you to select which column. But if you loaded the answer key in a different, say, in a different vector or in a different variable, then you can click from workspace. And then remember that the species list is contained in the vector species. So that's what I will use as the response, all right? And then I will add all. Okay, add all of the predictors, and then cross-validation. So we can put that there. Then we can just use the default here. And we can also set aside the test data. So maybe let's just say we set aside test data and say we want to set aside 30% of our data points for testing. Because we will be, so that means we will be training our algorithm using 70% of our data, and we will reserve the 30% of our data for validation to see what's the performance of our classification algorithms. Okay, so and then I'll click start session. Okay, so first let's look at the summary. It by default it will run the tree algorithm. So and then you see here model number one, that's a tree algorithm. It's just a draft. And then here are the hyperparameters that were used. So 100 splits were used. And then split criterion is Gini's diversity index. You can read about these in the documentation page. You have different options here. So it's just sort of a drag and drop thing. And then it tested individual features and so on. If you look at the scatter plot, now you can look at the a scattered plot of the original data set. For instance, here we can have column 1 and column 2, which are the sepal measurements. These are the distribution of the the measurements per class, so Setosa, versicolor, and virginica. And it seems to be not so discriminant among classes, because if you look at this middle portion over here, the virginica and versicolor variants seem to be mixed together. So that's why I knew from the start, since the beginning of the class, that it's not wise to use sepal width and sepal length as my as my attributes or my predictors in this algorithm. So if you want to first visualize the data and decide what are the nice or what are the best predictors or the best determinants of the class, you can play with the predictors options here. You can select the X column to be, say, 3 and say 4. And you will see here the usual picture that we are generating whenever using the third and the fourth columns only. But let's see what happens if I plot the second column in the X-axis and the fourth column in the Y-axis. So we get a scatter plot like this. Probably let's try the second and the third, get a scatter plot like this. The Setosa variant looks very isolated if we will use the second and the third columns, but it's still a mix-up between versinica and versicolor and virginica. Although you might argue that they are not too far apart from from this, but but at least we see accumulation of versicolors near the middle of this scatter plot, and then on the top right we see virginicas, and then on the bottom left really setosas are isolated. Okay, so this is how we analyze our data. So you'll see nice scatter plots, and you don't have to run any code. You just click and use the options available to the classification learner. Now, if you want to train different models, all right, you don't have to use individual codes, but you can just go here in the top ribbon again, then look at this portion, click the drop down option, and it will show you all of the classification models that you can use. You can use decision trees, logistic regression classifiers for nice enough data. You have naive Bayesian classifiers. You have support vector machines, KNN algorithms, kernel approximation classifiers, ensemble classifiers, and even neural networks classifiers. So there are powerful models within it. Then you can select one of them. Say, let's try weighted KNN. So you click KNN, and then you make sure that this is selected, the model number is selected, and then you can click train all, right, over here, so that all the models in the left panel will be trained using the data, right? So let's train all. The nice thing about the classification learner, it will do everything in parallel. So meaning if your computer has 4 cores, it can run it can train 4 algorithms all at the same time. it will use all the 4 cores or even 8 threads in your computer. All right. So here are the results. So the tree algorithm, which was selected by default, created this confusion matrix. Well, the confusion matrix worked like this, right? So here, you have here the number of setosa variants that are predicted as setosa. So the y-axis gives us the true class, while the x-axis gives us the predicted class. So that means 35 of the data were classified setosa. 35 of the setosas were rightfully classified as setosa. Now here, this number tells us that 33 versicolors were classified as versicolor, right? But 2 versicolors were classified as virginica. So you have some error there. Now the last numbers. So here we have 35 virginica, right? 33 of which were classified rightfully as virginicas, while 2 of them were classified as versicolors. So that's how the confusion matrix work. And that tells us that the accuracy of our tree algorithm is 96.2, right? And the optimized hyperparameters are used here. So it used a fine tree, 100 splits. It used a genus diversity index, and it didn't use any surrogate decisions. So you can look up in the documentation what these parameters are. Now, in the KNN algorithm, it's a little bit more accurate. It has accuracy 97.1%. All setosas were rightfully classified. Only 1 virginica was classified wrongfully, and still 2 versicolors were classified wrongfully. All right. So the total score is 97.1%. But note that I didn't put any parameter into KNN, right? I didn't tell the algorithm what is the K value to use and what's the kind of distance that should be used. The nice thing about the classification learner is that it finds the optimal hyperparameters for the problem. So if you look at the summary, so click model number, make sure you are in model number 2, click the summary, and it will give us the model hyperparameters. So use KNN or weighted KNN, and the optimal value for K that was found was 10. And the kind of metric that was used was Euclidean. The distance was Euclidean, and it used the squared inverse weight for the distance. So you see how much powerful the classification learner is, because you don't have to decide on our own what are the parameters or guess what the parameters are and then do the cross-validation later. Everything will be done automatically by our training algorithm, right? Now, if you don't know or if you haven't decided on what model to use, well, you can ask MATLAB to train all those easy algorithms. Let me just close these models. Can I close the models? Yeah. If I close all of the tabs, the models will be gone. So I will delete all the models here, okay, so that I can start from scratch. Or unfortunately, I can't start from 0 models. There's always a default model. But if you go back to the algorithm or the model options here, or the drop down for the models, you can click on all quick to train, or you can click all, so that it will train all classifier types, and then you can select which one is best among all of them. But it might take some time because you have seen there are lots of different algorithms here, and some of them might run longer than others. So you don't want to, say, spend a day doing everything. So you can play with it, but I'll just use all quick to learn, so that the learner app or the classification learner app will just run all those that are relatively quick to train. All right. I'll click this. And then let me all click it. Okay, sorry about that. I should delete this one. I should delete this one as well. And then I'll run train all. Okay, it will run a little bit fast because everything is done in parallel. So all my CPUs, all the cores in my computer are working independent jobs. And I think now all of them were done. And you see that on the left-hand side, you have a summary here, and the best algorithms were even highlighted, right? So the best ones are the medium KNN and the weighted KNN with 97.1% accuracy. So if you want to know more details about the models, you can just click on the models. A summary will be created for you. So here the hyperparameters used for the uh, for the uh, for the medium KNN. So you have KNN, 10 neighbors were used, Euclidean distance was used, equal weights were given for the distances, and the data was standardized. Even the pre-processing was done within the KNN algorithm. If you want to create a confusion matrix, make sure you are on the right model. I'm on model 3.5. I can use the confusion matrix here, and a confusion matrix will be generated. Then I can also click on the scatter plot. Okay. And then the query points are marked with an X. All right. So remember the training here was done for 105 data set. You can see the number of training data by summing up all the entries in the confusion matrix. So there are 35 representatives for each of the classes, so a total of 105. Oh, so that means the classification learner app really set aside 30% of our data. What's 30% of 150? That's 45. 45 data points were set aside for testing, 105 for training, right? And then here are the plots or the scatter plot of the training and testing data, and you will see the ones with an X are predicted incorrectly. Right. Now you can click on the others and generate similar reports. Let's see which one is lowest. Course KNN was the worst. It has only accuracy of 33.3%. Let's look at its confusion matrix. It was really confused, right? Because it predicted all of the testing data to be cetosis, right? But a third of them are versicolor, a third of them are virginica, so that netted only 1/3 accuracy. So this is something that you can play with for your final project. But before I go to the final project, do you guys have any questions about the classification learner? So I hope you can play with it because this is nice. Oh, by the way, you can export the model. So maybe that's the last thing I want to show you. So probably you choose which one of the trained models is the best. Say I chose model 3.5 with accuracy 97.1%. So I have KNN here. I'll click on the model here, and then I'll export model, right? So click the model, and then here in the tab, go here at the very last option here, you have export model, and then we can export the entire model to the workspace. So click export model, and then it will now appear in our workspace, right, as trained model. So now the trained model, named trained model, that's what I exported from the classification learner app. I think now I can use the predict command. So once everything is in the workspace, all I need to do is use the predict command and then put as first argument the name of the model that we exported from the learner app. So that's trained model. And then the second component would be the test point. And our query point is the vector y. Huh. Let me see. All right. We should use a different command. The predict model command will not work. The predict command will not work. So this is the one that we should use. Yfit equals trained model dot predict function x, where x is the predictor matrix. So I'm gonna copy this. Oh, by the way, our predictor matrix x should be what? I trained the data using 4 data point, using all columns, right? So that means I should put a vector here of 4 columns. So say 1.5, 1.4 centimeters, 2.5 centimeters, 5 centimeters, and 8 centimeters. And then there we go. Just enter that, and then you're gonna get the you will get the prediction that this specimen with the following measurements belong to the Virginica variant. Okay, so I suggest that for Thursday during class time we will not meet live, but I hope you guys can take some time to explore the trainer app or the learner app in preparation for the problem set. Okay. So are there any questions about the MATLAB codes I presented to you now? None? So let me just stop sharing. And then any questions about the any questions about the problem set? Okay, go ahead, Z.
Sir, good evening. Do we need to screen record everything, sir? Because I think that I saw a little bit of screen recording option the one that was posted on our website, but in the instruction for the problem set, there is no screen recording. So is it okay that we don't screen record everything?
Oh, yeah, that's fine.
Okay, thank you, sir.
Okay, other questions? Okay, so you still have lots of time to do the problem set, but that is if this is the only problem set that you have, all right? Good question, Jehan. When is the deadline? Well, I will suggest. All right, I'll decide now unilaterally without consulting Dean Zomer. Right? Hope he doesn't get angry with me. The deadline would be on the last day of the finals week, right? So when is our finals week? Mm, I just forgot the academic calendar. I think it's on the 21st. Is that right? June 21st? Let me double check that. But you can check the academic calendar whenever is the last day for the final exam. 5 p.m. on that day will be the deadline for the submission of the project. Oh no, let's not make it too confusing. 11:59 p.m. of the last day of the finals week will be the deadline for the problem set. Okay? Oh, June 14 is the last day, Jehan. I'm not sure about that, but yeah. So yeah, I thought it's one of my recording. It's one of my other reporting problem sets Z. But is this on the chapters that I was assigned, or was this instruction about screen recording about Dean Zomer's assigned topics? I didn't.
I'm not sure, sir, but it says clustering, so it's a bit similar to the one that was given to us. So
I see. Let me double check. Hold on, so that everything is everything is clear. So I handled Unit 2B. So if you go to our website, so let me share my screen for you to so that we are on the same page. Mumlinnet says the finals week is June 13 to June 21. So the deadline for the problem set would be on June 21, 11:59 p.m. So you still have uh, almost a month for the problem set. So use your time wisely because I know you have other classes to think about. So uh, uh, manage your time wisely, right? So I handled Unit 2B. So I can only speak about the assessment for Unit 2B. And okay, so it is here, problem set due April 21st. So I hope you already did this. And then I handled, did I handle 2C? Let me see. I didn't handle hold on. Yeah, I handled 2C. And you don't have to do this, all right? So let me edit this one. So you don't need to do this. You only do those that I sent via email. So because I don't want to delete this because this is probably Dean Jomer's notes. So probably he'll use it in the next iteration of the course. But I'll put it in brackets just to let you know, brackets, and then I'll read down. I'll make the red font. I'll make the font red so that you won't have to do this, right? So that's 2C, and then I did 3B, which is clustering algorithms. I hope this is vacant. Oh yeah, sorry. So yeah, Z, you don't have to do this. So for chapters that I handled, you only have to do, I think, two problem sets. Problem set NJAE01 and problem set NJAE02. And then for 3C, you don't have to do this either. Okay. All you need to do for sections that I handled, and they are units 2B, 2C, 3B, and 3C, all you need to do are the two problem sets that I sent via email. Is that clearer? Now I'm going to publish this. Okay, there should be it. So you don't need to do all of those in red font. In other words, all you need to do, hopefully I remember it right, you only have two problem sets under me, right? So problem set 1 and problem set 2, and that's it, right? So I will be grading for your problem set number 1 in the next couple of days. Probably that's how I will spend the remainder of the class days where we will not be meeting, or if none of you will be consulting. And on the 21st, I'm looking forward to looking at your projects. If you finish it early, then I'll give you the option to consult with me and ask for my feed forward, right? So you can submit a draft, but please tell me explicitly that what you are submitting is a draft so that I can comment on it and I'll give you feed forward, which is something that you can use to make it better. All right. But that is only if you finish it early. You're not obligated to submit a draft, all right? So, but if you want to make your project nice, because I'll give more weight to the second problem set because it's sort of an authentic assessment. I'll give more weight to it. And if you want to do good on it, you can submit a draft first, but in your email, please explicitly tell me that it is a draft and you want my comment on it. Then I'll give you some feed forward, some things that you can improve on. I'll tell you if it's already perfect and I'll give you a perfect score right away. If there are things that can be done, then I'll tell you what can be done, and you'll have time until the 21st to revise for work. All right? Okay, other questions or concerns? All right, so if there are none, it was nice. Having you during the semester. I hope you learned something. I still feel that I might have disappointed some of you that are well versed in data science because we really dealt on the mathematical tools that are necessary or that are used at the back end of data science. But again, the idea of the course is to give you a mathematical sort of understanding or a basic rudimentary knowledge of the basic mathematical tools that are used in data science, and we envision this course to be free for all. It's not like courses in other departments wherein you have to take lots of prerequisite courses just to get a data science course. We want it to be open to all. That's why we decided to just keep it simple. And probably what I can offer for those who are well versed in data science is an introduction to MATLAB tools that will help you do your work easier, all right, and more efficiently. All right. So that's it for the semester. But I still am looking forward to your projects or to your problem sets and looking forward to consultations. Just send me an email and we can schedule something, all right? And with that, that's the end of the class. Good luck, guys. Thank you for coming today. And I'll see you when I see you. All right. Bye, guys.
Thank you, sir.
All right. You're welcome.